So here we're going to talk about the most important distribution in all of statistics. It's the normal distribution. This is a continuous probability distribution for a random variable x. The graph is called the normal curve. Now, what does the normal curve look like? So we'll do it in red. It looks like a bell curve. Okay. Now, centered at the middle of this bell curve is the mean. So the mean properties of the normal distribution, the mean is equal to the median, which is also equal to the mode, the highest point. Now, if we go out one standard deviation each direction, so that's mu plus a standard deviation this way and mu minus a standard deviation this way. This point right here, these are called the inflection points. Okay, so that's the inflection point. Now, why is it an inflection? It goes from being concave down to being concave up. So why is concave down, concave up? What's going on there? I think a concave up, like a cup, it holds water, right? And I keep a concave down like a frown. I'm sad, I'm frowning, right? So that's kind of how I think about it. But it's the way that the curve bends. It has to do with the second derivative. You take calculus, you'll learn about concave up and concave down here. Now, the curve is bell-shaped. And it's symmetric, obviously, from the picture. About the mean. Okay? Number 3, the total area under the curve is equal to 1. So the area under the curve we will represent by this purple here. The area under the curve is equal to 1. So there's something I want you to start linking together from now on. Area is equal to probability. Okay? So whatever the area is, that's the probability. Area is equivalent to probability. All right? So that's what I want you to think of from now on. Area under the curve, all the area under this normal curve is equal to 1, means that of all the things that can happen, you're talking about 100%. Now, the normal curve approaches but never touches. It gets asymptotically close to this x-axis here, but it never does touch it. So it goes infinity in this direction and negative infinity in that direction. Okay? So the normal curve approaches but never touches the x-axis. All right, it gets asymptotically close, but it never does touch it. And then the last thing, you got your inflection points, which we already talked about. The inflection points at x equal mu plus or minus sigma. Okay, now if I go out another sigma, that's mu plus 2 sigma, and another sigma, that's mu plus 3 sigma. Okay, so this 3 sigma is a pretty big deal here, all right? You may or may not have heard it, but a lot of analysts, whenever they say this was a 3 sigma move, okay, they're talking about the move was greater, greater than or equal to 3 sigma, meaning it was really rare for that to occur. The percentage of chance that area under the curve right out here is small. It's really small, right? It's not like winning the lottery small, but it's pretty dadgum small, okay? So 3 sigma move represents something that's kind of out of the ordinary. So that's a typical thing you might hear somebody on TV, you know, maybe a stock move 3 sigma. That's very common for them to say something like that, you know, if they're describing an extreme move that doesn't normally happen. Okay? Now, there is a mathematical equation that models this where it has a mean of mu and a standard deviation of sigma. And that mathematical equation is this. It's called the probability density function. The PDF is equal to y equals 1 over the standard deviation times the square root of 2 pi. That's weird, right? That is actually a constant that we multiply to make sure the area underneath is 1. Pretty interesting. And this is e raised to the negative, and in parentheses, it's x minus mu, the deviation of the values from the mean, squared, divided by 2 times the variance. Okay? So this equation is a normal curve with mean equal to mu and standard deviation equal to sigma, okay, in general, all right? Now, there are many parameters, okay? So there are many parameters going on here. So many that there's 2 of them, right? 2 parameters determine the shape of the normal curve. There's only 2 parameters. Those parameters are the mean and the standard deviation. The mean gives the location of the line of symmetry. The mean mu gives the location. The standard deviation, sigma, tells how spread out the data is from the mean mu. Okay? So it gives the location, the line of symmetry. Now, there are many normal distributions. In fact, many means infinitely many. Why? Because all we need to do to create a new normal distribution is come up with a new mean and a new standard deviation. And if we do that, then we got a new normal distribution. So with mean mu and standard deviation sigma. But, and this is a big but, there is only one standard normal distribution. There's only one standard normal distribution. And the standard normal has a mean equal to 0 and a standard deviation equal to 1. Okay? So the mean is equal to 0, and the standard deviation is equal to 1. So that really complicated formula that we had up here, what does it become? It becomes 1 over the square root of 2 pi e to the negative x squared over 2. Okay, so that formula simplifies a little bit. And if you graph that formula, okay, so say I graph that. So 1 divided by the square root of 2 pi, and then I have e raised to the negative x squared divided by 2, enter, and I graph that. That's what the curve looks like. That is the normal curve, people. So it comes down, it comes up, and then it goes down just like that. So it's really stretched out here, right? But that's what the normal curve looks like. I wonder if I could change the zoom. Let's do, can I do a custom zoom? Not sure I can do a custom zoom. Oh well. But yeah, that's what the normal curve looks like. Okay? So there's only one standard normal. So you would say the standard normal versus a normal distribution. Because there are many normal distributions, but there's only one standard distribution, standard normal distribution. Okay? So there's a difference there. Now, let's graph some of the normal distributions. So the question becomes, which normal curves have the greatest mean, the greatest standard deviation? Okay? So here's an example of just 3 normal distributions. Now remember, to get a normal, we need a mean and we need a standard deviation. The mean is where the line of symmetry is, right? So it looks like my line of symmetry is right here. So I have a mean of 3. Okay, line of symmetry here looks like it's a mean of 2. And a line of symmetry here looks like it's a mean of 4. So which one's the greatest mean? Distribution A, distribution B, or distribution C? It looks like distribution C is the greatest mean. Okay. Now what about the greatest standard deviation? Okay, what about the greatest standard deviation? So standard deviation, that's how spread out we are. So the more we're spread out, the larger the standard deviation is. Well, how do I tell how spread out we are? I'll look at the peaks. I'll look at how tall the distribution is. Okay? And to me, it looks like the most spread out distribution happens to be C. So this has the greatest standard deviation as well, because as you can see, the distribution is spread out from the mean further than any of these other ones. So maybe, and I'm just making these numbers up, but maybe this standard deviation is like 2. Okay? This one, so this is like the lowest. That's like the second lowest, and that's like the third, right? That's the high one, right? So this one has the smallest standard deviation because most of the data looks like it's centered around the mean. The higher the peak, the smaller the standard deviation. So maybe this one here is like a standard deviation of 1, and this one here is like a standard deviation of 0.5. Okay? So that's the idea there. So you look at the peaks, and the higher the peak, that means like the more we've pinched up the graph, so where most of it is centered in one spot, so it's a small standard deviation. Whereas if you flatten it out, the more you flatten it out, the more flat it becomes, the more spread out your data gets, and then the higher your standard deviation becomes. So this one has not only the greatest mean, but it also has the greatest standard deviation. All right? So the normal, the standard normal, what does this look like? The standard normal graph has a mean, mu equal to 0, and a standard deviation, 1. And so this is what the curve looks like. Okay, so this is what the standard normal curve looks like. That's the standard normal curve. It has a mean of 0 and a standard deviation equal to 1. Okay, so once you go out about 3 standard deviations, you pretty much got all of the area that you'd be concerned about. Okay, so hopefully this is a good little introduction for you into the standard normal curve, which there are infinitely many standard normal curves, right? But there's only one. I'm sorry, there are infinitely many normal curves, but there's only one standard normal curve. Okay, so only one standard normal curve, and that's that curve right there. All right, guys.